Hello. Welcome to the next lectures in the series of optical spectroscopy lectures. And we are going to start in the next video with the fluorescent spectroscopy. And we are going to devote a couple of videos to the fluorescent spectroscopy. And we'll start by looking at the processes that are occurring in the molecules that can be detected with fluorescence, and also for the ones that can't be detected with fluorescent spectroscopy, to understand more the processes on the molecular levels. So the reason why we are talking about fluorescent spectroscopy here in general is that it is one of the spectroscopy types in the optical spectroscopies. It is complementary to UV visible spectroscopy and IR spectroscopy, and it is dealing with a slightly different kind of processes. Here we are measuring light that is emitted by the molecules. And going a bit ahead of what we will be seeing here, the reason why it is so important is that fluorescence is one of the methods that allows us to detect the smallest quantities of molecules. There are even single molecule fluorescence spectroscopies available. So this is why it's extremely relevant. So to start understanding what is going on in fluorescent spectroscopy, we have to take a look into the electronic states of the molecules. And in the ground state, there are two types of electronic arrangements. So the electrons in the molecule can either be paired or they can be not paired. And in the normal ground state molecules, the electrons are paired. So we say that they are in the singlet state. However, some molecules, such as free radicals, are in the diplet state. This means that the electrons are not paired. This is also the reason why radicals are having paramagnetic properties, while most molecules have diamagnetic properties. In the optical spectroscopies, we are, however, also interested in the excited species. So this means that when the molecules are absorbing light or heat, then they can be brought up to an excited state. And in the excited state, there are also two possibilities that the molecules can be occupying, either an excited singlet state. This is a state where the electrons are still paired, even though one of the electrons has been excited to a higher energy level. Or they can be in the triplet state. This means that the electrons are not anymore paired, and this is called then the triplet state. So mostly what we will be observing is excitation to the singlet state. However, excitation to the triplet state is also important, but it is much, much rarer due to the fact that the lifetimes of the excited triplet states are much longer. So this process is extremely much less probable than the excitation to the singlet states. So mostly what happens due to excitation is an excitation to a singlet state. It is important to mention that if the triplet states are populated, then the excited triplet states have a lower energy than the corresponding singlet states. So let's see what happens on a molecular level when we are carrying out the excitation. So in the room temperature, most of the molecules are on the ground state, and they are vibrationally and rotationally not excited. So they are sitting on the level, ground state level, what we call a S0, and their vibrational excitation level is usually also V0, so denoting that vibrational excitation has not happened. And when now these molecules are exposed to light source, especially intensive light source, then the compounds can absorb light and become excited. So this means that the electrons are brought up to a higher energy level, and mostly the excitation occurs now to the singlet excitation levels. So either S1, which is the first excited level, or to S2, which is then the second one. And additionally, also molecules can become vibrationally excited. So for example, if we would say that a quant has been absorbed by the molecules that is in energy equal to this transition that is denoted here on the scheme, then we would say that the obtained energy level of this molecule after absorbing light is S2, denoting that it's second electronically excited level, and it's also a V3 state. So this means that it's vibrationally the third level. We can also have rotational excitation levels in addition then to the vibrational excitation. So this denotes that the molecule, as a result of absorbing this light quanti, becomes electronically excited, but also at the same time vibrationally excited. And usually the singlet transitions are the ones that we will be observing. So either excitation to S1 or S2, and then the corresponding vibrational levels. So singlet triplet transfers are usually directly not observed, but they can be populated due to other processes. Now, when the molecules are in the excited levels, then there are a number of different mechanisms according to what the molecules can return back to the ground state. And we will have a look at these processes now on the following slides. We will, on the scheme, denote the deactivation processes depending on if they are radiation-less, so meaning that no quanti are being emitted as a result of these processes, or if they do involve emission, then we denote this as well. So the radiation-less processes we denote by these types of lines here, arrows here, and so dashed arrows, or the processes that occurred via emitting a quanti, we denote with this line arrows. The luminescence processes, so both fluorescence that we are focusing here primarily, as well as phosphorescence, are limited to the conditions where the radiation-less processes are slowed down, at least some of them, so that we can actually observe the processes where photons are emitted. So this is very important that we would actually have these conversions that are shown with the straight line arrows. So what are then the processes that what are contributing for the molecules to return from the excited state to the ground state? The first thing that usually happens with the molecules is that they are vibrationally relaxed. So this means that when we have the molecules excited in the first place by absorbing the light quanti, then they obtain both the electronically excitation as well as vibrational excitation. And the first thing that happens is that the molecules lose their vibrational excitation. So this means that they return from the S2V2 to the S2V0. And this happens on all of the levels where the molecules is excited to either to S2 or S1. You can see that the molecules return to the vibrationally ground state. And this is happening extremely fast. The lifetime of these vibrationally excited species is one of the lowest in all of these processes. It's about 10 in the power of minus 12 seconds. This means that almost immediately when the excitation has happened, the molecules return to the vibrationally not excited state, but the electronic excitation still remains. And this means that if fluorescence happens, for example here, when the molecule is excited from S0 first to S1 V5, for example, then immediately the molecule returns to S1 V0. And if fluorescence is following this process, then the fluorescence is happening from S1 V0. That means that the fluorescence quanti that is emitted by fluorescence, so returning from S0 to the electronically not excited state, so the electronic ground state, is always of less energy than the quanti that brought about the excitation. This means that the fluorescence wavelengths are higher in wavelength than are the wavelengths of the light that was absorbed first to bring about the excitation. However, in addition to the vibrational relaxation, there are also other processes that can happen. So one of the important ones is also internal conversion. This means that if we have multiple electronic excitation states, so for example S2 and S1 here, then it is possible that the molecules goes from S2 state over to the S1 state. This is more likely when the electronic excitation states S2 and S1 are very close in energy, so that the vibrational excitation levels of S1 actually overlap with the electronic excitation state S2, like we see it here. So when the molecule is excited from S0 to S2, V3, for example, then the first thing that happened was due to the vibrational relaxation that the molecule returned to the S2 V0. Now, the S2 V0 is overlapping in energy with the S1 electronic excitation level with a vibrational excitation of V1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the S2 V0 is overlapping with S1 V10. This means that they are very close in energy, and the molecule can go from S2 V0 to S1 V10. So it's very probable that the molecule hops from this state to this state here. It's not fully understood why this is occurring, but it's known that it is a very, very likely if these energy niveaus are overlapping. And what happens then is that this is now again a vibrationally excited niveau, and from here the molecule can additionally vibrationally relax. So the molecule can go down in vibrational excitation and end up on the S1 V0 niveau. So that means that it's still electronically excited, but it has lost now the vibrational excitation. The lifetimes of the S2V0 niveaus that can then hop to S1 vibrationally excited niveaus are about 10 in the power of minus 6 to 10 in the power of minus 12. So they are slower processes than are the vibrationally exciting niveaus. So this is why it is possible that from these niveaus we now also start observing fluorescence, and we don't observe fluorescence from the vibrationally excited niveaus. So if the fluorescence is occurring, then it's most likely that it occurs from the S0 V0 on this electronic scheme that we have here on the right-hand side. And interestingly, for very many molecules, due to the internal conversion between the S2 and S1, independent of the excitation wavelength, we still see one band in the fluorescence. So independent of either we first bring about S0, S2 excitement or S0, S1 excitement, the fluorescence is corresponding to the emitting of a photon by molecule going from S1 back to S0 ground state. So we don't see a transition from S2 to S0, but we see a radiation-less internal conversion from S2 to S1, followed by a vibrational relaxation, and then we could see a fluorescence from S0 to S1 level. However, this is competed by the radiation-less conversion from the S1 to the ground state. So if the molecule has a very wide vibrational excitation levels on the ground state, like depicted here, then it is possible that the electronically excited S1 V0 also converts with an internal conversion to the S0 and corresponding vibrationally excited state here. And this is, of course, competing with the fluorescence. And here it is determined by the lifetimes of these species, lifetimes of these processes, which of the process we actually see in our samples occurring. It is also possible that the molecules lose their excited states due to the external conversions. This means that the electronic excitation is lost due to the energy transfer from our excited state molecule to either solvent or other species in our solutions. And this is one of the facts that is supporting this mechanism is that there is solvent effect on the fluorescence intensity. This means that different solvents are of different efficiency in contributing to the external conversion, and therefore when we do measurements with different solvents, we also can observe different fluorescence intensities. Additionally, environmental factors that are determining how frequent are the collisions between our excited molecules and the solvents or other solutes are influencing the fluorescence intensity. So these are temperature and viscosity of the solution. So at lower temperatures, the collisions are less frequent, and therefore usually we see higher fluorescence intensities. This means that by slowing down the collisions between the molecules in the solutions, we are reducing the probability of external conversions, and therefore fluorescence becomes more likely. Additionally, viscosity is important. So less viscous solutions are solutions where there are more collisions between the excited analyte molecule and the solvent. So the more viscous solutions are less likely to undergo external conversion, and therefore fluorescence is more likely in these solutions. What is also possible is that if there are, in addition to the singlet states, there are also excited triplet states. these are not depicted here on this energy diagram, but they exist. And if there are conditions that prolong the lifetimes sufficiently, then there is possibility that from the excited S1 state, so from the singlet state, there is a transition also to the triplet state, T1. And this is most likely for molecules that contain heavy atoms. And the triplet states are important because from triplet states, it's possible that there is a phosphorescence occurring. So this means fluorescence and phosphorescence are very similar. Phosphorescence means that the molecule returns from the triplet state to the ground state by emitting a photon again. But the difference between fluorescence and phosphorescence is that in fluorescence that occurs from the excited singlet state, while in phosphorescence that occurs from the excited triplet state. And the difference is in the lifetimes of these species. So the T1, so the triplet excited species, have lifetimes of up to a few seconds. And this is why phosphorescence is observed, for example, very often for solids. And these are also the processes what you see if some kind of a material is first irritated by, for example, ultraviolet light, and then they are emitting light over multiple minutes, for example. So these are usually phosphorescence processes. So this is the difference between the fluorescence and phosphorescence. Now, what we are usually observing in solutions are the fluorescence processes, and fluorescence is extremely widely used in analytical chemistry. So we are talking mostly about fluorescence in the coming parts of this in these lectures. The importance in understanding if the molecules do fluorescence or not is associated with the likelihood of other competing processing. So if the internal conversion or external conversion are very, very likely, then the likelihood of fluorescence is simply decreasing. And the lifetime of the processes of the species is very important here. The processes with a lower lifetime are more likely to occur. So the faster the process, the more likely it is to occur. And therefore, the quantum yield of fluorescence can be determined as the ratio of the rate constants of fluorescence divided by the sum of the rate constants of all of the competing processes. So fluorescence, as well as internal conversion, external conversions, as well as other processes that could compare. For example, phosphorescence or dissociation or anything else. So in the cases where fluorescence is occurring with a very high quantum yield, sometimes the quantum yields can be close to 1, for example, then this means that the rate constant of fluorescence is by far the dominating process. This usually happens by slowing down the other competing processes. And this is often determined by the environmental conditions or by the structure of the compound, as we will see later. So this was a short introduction to the energy levels of the molecules and how these are all playing a role in the fluorescence when we are doing our fluorescence measurements. In the next videos, we are going to look into the compounds that are fluorescing, as well as the instrumentation and some brief introduction into the applications of fluorescence spectroscopy.